For this example, we consider the table which contains the value of the n and the f of n. As you see the n values, the 15.5, 15.1, 15.01, 15.001 is getting closer and closer to the value 15, where the value of the function at n are starting from 87.5 at n 15.5, and then say 87.1, 87.01, 87.001. As we see the pattern, we can predict that f of n approaching to the value 87. So we can see that the n approaching 15, f of n approaching 81, but make observation for the n 15.5, 15.1, 15.01, 15.001 approaching to 15 from the right side, because all the values here greater than 15. So come back to the set of the questions here. Given that a is an integer, determine the value of the a from the notation limit of the function fn as n approaching a positive. That means n gonna be greater than a. In this case, we can see that the a that we are looking is 15. And then for part b, if we are going to find the limit of the function f of n as n approaches a positive, you see n approaching 15 positive, the f of n approaching to the value 87. When we put these two together in the limit notation form, we can say that limit of the function f of n as n approaches a positive, or the limit as n approaches 15 positive, or from the right side of the 15, or the right hand limit, the value approaching 87. So that's the answer. So to wrap up, in part A, the value a that we're looking for is the 15, and the limit of the function from the right is 87. For the next example, we have the function f of x equals x squared minus 1 quantity divided by x minus 1. As you see, this is the rational function. I'm going to put a note here. Rational, or the ratio, or another way, like polynomial over polynomial. Rational function. When you have the rational function as the expression divided by the other one, the restriction comes from the bottom, where the bottom cannot be 0. In this case, gonna protect us to get the value x equals 1. Because if x is 1, the function is undefined. Our goal is to approximate the limit by filling the table and then round to the nearest thousands. That means round to like 3 decimal places. As you see the two tables, the one from the left, the x value 0.9, 0.99, 0.9999, and 0.999999. That pretty much like x approaching to the value 1 from the left side, because all the values of the left table here less than 1. So we're going to consider the left hand limit of the left table. At the same time, for the right table, x 1.1, 1.01, 1.001, 1.0001, getting closer to 1, but coming from the right side. So therefore, we look at the right hand limit of the right table. The function value gonna be from the quantity x squared minus 1 over x minus 1. As we know that x cannot be 1, the values that we have on the tables, they are not 1. None of them equals to 1. Either like less than 1 or greater than 1, but approaching to 1 from both sides. So as is not 1, the technique of this one is, if we have x squared minus 1, from algebra class, this expression can be factored as x plus 1 times x minus 1. As the quantity x squared minus 1 divided by x minus 1. So the factor form also divided by x minus 1. We can see that these factors are reduced. Therefore, this expression is simplified to be x plus 1, but we have to make a note that x cannot be 1 in order to use this simplified form. From the bottom cannot be 0. Therefore, whatever expression we have here, we can use the simplified form as long as x cannot be 1. Okay, so x plus 1, the shortcut to complete the table. As x is 0.9, added by 1 can be 1.9. And next 1.99, 1.999, 1.999999. And then the right table, we do the same way. 1.1 plus 1, that becomes 2.1, 2.01, 2.001, 2.000001. As the table are completed, so we look at the value of the function as x approaches 1 from the left, the value approaches to the value 2, as we see the trend of the numbers here. And for the right table, as x approaches 1 from the right, the value of the function approaching the value 2. So now we have the one-sided limit from the left side, from the right side, coming toward to the same value 2.